Vehicles running on alternative fuels need a range of travel comparable to gasoline vehicles, something greater at about 300 kilometers, 200 miles, before they will be adapted for general use. Unfortunately, hydrogen has the lowest energy content per unit volume of any fuel. To carry enough hydrogen for an adequate travel range, a vehicle must either compress the hydrogen gas, liquefy it, or absorb it onto solid particles. To match energy contents with natural gas, hydrogen must be compressed to a much higher pressure. A tank filled with 10,000 pounds per square inch hydrogen holds the same amount of energy as one filled with 2,000 pounds per square inch of compressed natural gas. Under such pressures, hydrogen is such a small energetic molecule that it diffuses through most materials that line the walls of compressed gas tanks. Once hydrogen penetrates the liners, it reacts with many wall materials and weakens them. Lightweight storage tanks that can withstand hydrogen at 10,000 pounds per square inch have liners of high molecular weight polymers and walls of filament-wound carbon fibers and have shapes that are nearly spherical. Not only do such tanks cost roughly $3,600 in large quantities, but their shape does not fit easily into vehicles, a round peg in a square hole. Finally, the energy required to compress hydrogen to 10,000 pounds per square inch equals about 15% of the energy value of the hydrogen in the tank. Fuel cells today require some very expensive components. In particular, the electrocatalyst and proton exchange membranes are literally worth their weight in gold. A catalyst is a substance that promotes a chemical reaction without itself being consumed. As such, it must remain chemically inert under the conditions necessary for the reaction. Nearly all electrocatalysts for hydrogen fuel cells contain platinum, a chemically inert metal that costs over $35 per gram, substantially more than the price of gold. At present, a typical fuel cell vehicle contains over $70,000 of platinum. Vehicles must function dependently despite being subjected to a constant vibration, rapid temperature changes extending from cold starts to high running temperatures, frequent bombardment with dirt and water, and occasional neglect or incompetence. Hydrogen fuel cells may not be ready for such abuse. Their membranes must be thin to attain sufficient permeability, but this increases their fragility. Their catalysts must have a high surface area to attain sufficient reactivity, but this makes them more vulnerable to contamination by dirt or poisoning by carbon monoxide. To sustain operation, a fuel cell must be just right. Not too wet, not too dry, not too cold, not too hot. Aside from the technical difficulties in developing an affordable and reliable vehicle based on hydrogen fuel cells, is the daunting task of expanding the infrastructure for hydrogen production and distribution.